I sometimes get feedback from students that Kirchoff's rules are really difficult to use. And I think the reason that I get that feedback is not because the rules themselves are difficult, but because we often apply them to the more difficult circuits to solve. If we have simpler circuits that are just combinations of resistors in either series or parallel or some combination thereof, but strictly series and parallel, we often will not use Kirchoff's rules in their raw form. We'll use the equivalent resistance equations, which actually are derived from Kirchoff's rules. And so in those more complex circuits, we end up with more complex equations, sometimes with more than one unknown, and we have to solve using systems of equations. And I think that's really what people find difficult. So to try and avoid having the difficulty of the algebra influencing people's thinking about how difficult Kirchoff's rules are, I wanted to do some more examples, but this time with simpler circuits that you might just use the equivalent resistance equations to solve a little more rapidly. But we can apply Kirchoff's rules here and solve these without getting bogged down in some of the tricky algebra. I have a separate video that I'll link in the description that explains Kirchoff's rules in some detail, but just as a basic refresher, the two rules are written out as equations at the bottom of the screen here. So this first one, the total delta V equals 0, just means that if we pick any closed loop to get through our circuit, and that closed loop starts and ends at the same point, and we track how the electric potential changes, or how our voltage drops or increases as we go around that circuit, we'll find that getting back to our original position also gets us back to our original value for electric potential. So the total change in electric potential, the total potential difference for any closed loop, is going to be 0. Now, electric potential is a property of just a location within our circuit. So there is some value for electric potential at some spot, say 10 volts. And it doesn't matter where I go from there. If I get back to that spot, I'm going to get back to a position where we're at 10 volts. So any changes that I go through have to end up getting me back to 10 volts. For the and that, by the way, is just an application of the conservation of energy idea, that we have a certain amount of energy in our circuit, in our system here, and having our charge go through this circuit can't increase the amount of energy or decrease the amount of energy. If we had anything other than delta V equals 0 for that loop, then our charge could just go through the loop again and again, and let's say we had a positive delta V, it would gain energy every time it went through that loop. And so we just send that through a bunch of times, and we eventually have infinite energy, and we can power the entire world on and the entire universe on a single circuit. Be handy, but not possible. The other one, the total current in equals the total current out. That's true for any point on our circuit, but we'll typically just apply it to junctions, places where we have wires coming together or wires splitting apart. So maybe we have a single path splitting into 2 or 3 paths, or 2 or 3 paths converging down to a single path. The idea here is that current is just a measure of how many charges are coming in for every second. And so if we have a certain number of charges coming into a spot every second, we have to have the same number of charges leaving that spot every second. Otherwise, we get this buildup of charge at that one location. And a buildup of charge wouldn't make sense there because they would all be the same negatively charged electrons, and they would want to repel each other. So they would push away from one another. If that weren't true, then we let that circuit run long enough, and eventually we get, infinite charge at some location, which again can't happen. So now let's apply those two ideas to two fairly simple circuits to solve some problems with Kirchoff's rules. So in our first circuit, we've got just 2 resistors. Those 2 resistors are in series. So if we knew values for those 2 resistors, we'd just add the 2 individual values together to get the equivalent resistance for our circuit. We could then set the current equal to the total voltage dropped through those resistors, which would be 10 volts, divided by the total resistance of those 2 resistors, and that would have to be equal to our current. And so we could actually solve this one using the equivalent resistance equations fairly simply. But we're going to write this out instead using Kirchoff's rules. Actually, this one, it's not going to be too interesting to use the junction rule because there's no splits in the path. We have just a single path all the way around the circuit. So the junction rule just tells us that the current through each one of these components has to be the same. The current going into R1 has to be the same as the current coming out of R1, and that has to be the same as the current going into R2, and that has to be the same as the current coming out of R2. So the current all the way around here is the same value, and we're told that the current through one spot is 0.1 amps here. So that's the current everywhere else. Now the loop rule is going to be where the action is on this one. So the idea is if we pick a point to start at, and let's say we'll start at this spot right here, and we go all the way around our circuit, that as our voltage, as our electric potential changes, as we have voltage across components, our total change as we get back to our starting point has to be 0. So let's say as we go around this path, we start out by going through this battery, and we're going to have a plus 10 volts there. We're going from the short side to the long side of the battery symbol, which means we're going from the low energy to the high energy, the low electric potential to the high electric potential side. So we add 10 volts from that change. Then we get to this resistor, R1. And resistors are going to cause a decrease in electric potential. There's a voltage drop across resistors. Now, if I were going backward in my tracing here, if I were going the opposite direction as current, then I would be going from the low energy or the low potential to the high potential side. But here I'm going in the same direction as current, so I'm going from the high to the low. So we're going to have a drop across this resistor of some negative value. Now, or drop of some value of electric potential, so we'll say it's a negative change. And let's say that's going to be just delta V1 to go with R1. And then for R2, same deal. We're going to lose electric potential here, so we'll have negative delta V2 on this one. We then continue on our way and we get back to our starting point. So we have 3 places where the electric potential changes. And we know that the electric potential altogether has to change by 0. So that would mean for us that we can write an equation, the total voltage change or total electric potential change is equal to 0. And that's going to be a plus 10 volts from our battery. That's going to be a negative delta V1 from that first resistor and a negative delta V2 from our second resistor that have to add up to 0. Now using Ohm's law, we can also say that delta V is equal to the current times the resistance, so the current through some resistor times the resistance of that resistor. So I can substitute those delta V terms up here. So I'll leave the plus 10 volts alone. We'll have a negative, and then the current through that resistor R1 is 0.1 amps. That's the same for everything here. Oops, 0.1, not 0.01. And then the resistance is 20 ohms. And then over on this one, we're going to have negative current, again, 0.1 amps. And we don't know the resistance, let's just call it R2. And that's equal to 0. So simplifying this equation, we have plus 10 volts, and then minus 0.1 times 20 is going to be negative 2 volts. And then minus 0.1 amps times R2. That's equal to 0. So on the left side, I have a positive 10 volts and a negative 2 volts. That's a positive 8 volts altogether. Positive 8 volts. And then I'll add that 0.1 amps times R2 to both sides. So that'll be equals 0.1 amps times R2. And divide both sides by 0.1 amps, and I find 8 volts divided by 0.1 amps is 80 ohms. And that is the value for R2. This next circuit is a little trickier. Still not too bad. We only have one battery. That's where things get really messy on these, is if we have two batteries or two potential different sources. So on this one we have 3 resistors. We've got a little bit of parallel, we got a little bit of series on this. You could still solve this one by doing the equivalent resistance equations and Ohm's law alone. But we're going to solve using Kirchoff's rules without that derivation that's been made for equivalent resistance for series resistors or parallel resistors. Now this one we actually do have a split in our current. So it's going to be useful to write a junction rule equation on this one. We have one current labeled already. I'm going to go ahead and label the other 2. The current through R2 is labeled as I2, so I'll call this one through resistor 1, call that I1, and then this one will be I3. And the junction rule says that at any spot where we have a split, the current going in and the current coming out have to be the same. So we have a split right here. Current going into that is I1, and coming out we have both I2 and I3. Alternatively, we could look at this spot. We have current coming into that as I2 and I3, and the current coming out doesn't change, doesn't change, doesn't change, and we see here it's labeled as I1. So either way, we can write an equation for the junction rule that I1 equals I2 plus I3. All right, and then we have the loop rule to consider as well. Oh, and on this one we actually do know one of those values. We might as well plug that in. I1 equals 0.25 amps plus I3. Okay, so if I figure out one of those currents, I'll have an easy time figuring out the other current. But I don't have any information to do that right now just from this equation. I'll have to look to the loop rule to continue this. So for the loop rule, we now have a little bit more work to do simply because we have more loops that we could go through. So we have 3 potential closed loops that we could go through on this one. It turns out we'll only need to do 2 of these, but we could do more if we needed to. So the first one, I'm going to start right here, and I'm going to go through that battery first. So I'll just kind of write the equation as I do this. So going through the battery from the short side to the long side, that's going to add 20 volts. All right, and then we continue around our circuit, and we go through this resistor R1. So that's going to decrease our electric potential, and the change on that is going to be the current times the resistance. We know that from Ohm's law. The current on that one we call I1, so this is a negative change, so it's I1 times the resistance, which is 20 ohms. And then when I get to this point, I have a choice. I could go through R2 or I could go through R3. Let's go through R2 on this one. So through R2, I have another change. That's going to be another decrease in electric potential. And the amount is going to be current times resistance. Here we know both of those. So that's 0.25 amps times 40 ohms. And then we continue along, and let's go back toward our starting point here, and we don't encounter any other places where electric potential would change. So then our total change in electric potential has to be 0. In this equation, I see I have only one unknown, so I'm in good shape there. Let's go ahead and solve for this. Plus 20 volts on the left there. And then we don't have anything we can do to simplify this term. So negative I1 times 20 ohms. And then minus, we've got 0.25 amps times 40 ohms. So that'd be minus 10 volts equals 0. So I've got a plus 20 volts and a minus 10 volts. That gives me a plus 10 volts altogether. And a negative I1 times 20 ohms. Let's add that to both sides. So equals I1 times 20 ohms. And then dividing both sides by 20 ohms, I find that I1 is equal to 0.5 amps. Now with that information, I can come back over to my junction rule equation. I now know that I1 is 0.5 amps, and that's going to be equal to 0.25 amps plus I3. And from there I can subtract 0.25 amps from both sides, and I find 0.25 amps equals I3. All right, so I know almost everything here. I still don't know a value for R3, so I still have a little bit of work to do on this one. We know the current through R3. We haven't established yet what the potential difference across R3 would be, although since it's in parallel with R2, you might recognize that it's going to be the same as the potential difference across R2, so you can solve for that. Let's just go ahead and write another loop rule equation, though. We might as well get some practice with these. So I'm going to go through a different loop, and this time my loop is going to take me through that R3 resistor. And so let's, I need a little space here. There we go. Let's start in the same place we did before. So we go through our battery, and the very first change then is going to be a plus 20 volts. All right, and then through this resistor R1, so that's going to decrease our electric potential by an amount equal to I times R, delta V equals I times R. So that was I1, which we said was 0.5 amps, times the resistance, which is 20 ohms. We figured out that 0.5 amps in the last step. And then we're going to go, instead of through R2, let's go through R3. And so we're going to have another change then. It's going to be a decrease, so a negative, and it'll be I3, which we said was 0.25 amps, times R3, which we don't know. And then that continues along, and we get back to our starting point without having any other changes in electric potential. So that's got to be 0. Simplify this, and we'll solve for R3, which is our ultimate goal. So plus 20 volts, 0.5 times 20 ohms is 10 volts, and that's a negative 10 volts, plus a negative 0.25 amps times R3 equals 0. Plus 20 volts and a negative 10 volts gives us a positive 10 volts. And I'll add that 0.25A times R3 to both sides and get us just 0.25A times R3 all by itself on the right side. And then when we divide both sides by 0.25 amps, we have R3 on the right side by itself and 40 ohms on the left side. And that is ultimately the answer we're looking for. So Kirchoff's junction rule and Kirchoff's loop rule, by themselves, not especially difficult to write. We do have to be careful about our motion through the circuit, but the equations aren't typically too bad to write. We really can get bogged down in some pretty tricky algebra, though, in some of the more complex circuits. And that's where this one is really difficult, is just getting used to doing some of that more difficult algebra. Thanks very much for watching. If you learned something from this, I would encourage you to like or subscribe to this so you can see future videos pop up in your feed. Have a great day.